That was a very nice introduction, thank you. And he's right, I did work for a long time for the British Geological Survey, and I had a thoroughly enjoyable time working there. It converted me from, I guess, a theoretical experimentalist, where I had spent most of my undergraduate research and PhD research looking at analogue type experiments using materials that are not real rocks, into somebody that actually worked with real materials. So I started looking at engineered materials and host rocks that are barriers to flow in the subsurface, and that's what I want to talk to you about today, how we can use geology to dispose of hazardous waste products. So my interests did originally start in understanding heat flow and dike injection and crustal rheology, but I've since moved into a research area where do I need a lapel mic?
I know, I just...
Okay, well, John A might not be muted. John A can mute himself when he arrives. Okay. Sorry, lost my train of thought. Okay, so I've, since working at the BGS, started looking at real rocks and understanding how they can be barriers to subsurface flow rather than conduits of flow. And to that end, I ran a lot of experiments at the survey, which I want to talk to you about today. And since I've been at Cardiff, as Chris says, I joined just under 3 years ago, I've been setting up a lab in the basement to do similar types of experiment, and that's getting there, but it's a slow process, because the type of equipment that you need to push fluids through rocks and measure the properties of those rocks is quite bespoke and expensive, and it takes a long time to establish. So we're getting there, and hopefully I'll have new results from my Cardiff lab soon. Is this going to move forward? No, I'll click. That's going to be annoying if I have to do that. So really, I wanted to explain some of the motivations behind why you would care about disposing of waste products in the subsurface. And that really comes back to energy usage and how, as a society, we need to move away from using fossil fuels and using renewable...
Sorry to interrupt, but we at home don't have any sound.
You look like you're muted.
Hello, can you hear us now?
Yeah.
Excellent. Okay. Fortunately, you didn't miss much. Okay, so why do we need renewable energy sources? Well, we all know that we're experiencing changes in the Earth's climate, and that's leading to degradation of habitats. It's leading to extreme flooding and heat events, and we know all about why we are polluting our environment in a way that is not sustainable, and we need to move to using fewer fossil fuel reserves for our energy use and towards sustainable resources. And so that could be things like wind or biofuels, but it also could be other low carbon sources like nuclear power. Is this actually plugged in? I don't know why that's not. Okay, if I click, will it move? No, I'm going to have to click there. Okay. But if we do use nuclear sources for our energy, and nuclear is a great option for baseload, because once you turn on a nuclear power station, you can produce consistently a large amount of energy, and once it's ramped up and got going, then it'll just carry on. But it's less good for dealing with fluctuations in demand, and for that you might need renewables. So if we look to the future, we might need to have an energy picture where we use renewable sources and nuclear energy as a way of producing the energy that we need for society. But when we produce energy by this method, we do produce waste, and that waste needs to be safely disposed of. So even if we don't move to using nuclear fuels, we still need to dispose of waste, and we will still need to use geology and the types of materials that I've been investigating in order to be able to do that. So that could be because we are producing a lot of domestic waste that needs to go into landfill, and we need to protect our environment underneath that landfill site by using engineered geomaterials like bentonites. Or it could be that we want to carry on producing our energy from fossil fuels like gas from the North Sea, but that produces CO2, so we might need to dispose of that, and for that we need subsurface geology as well in order to prevent emitting it to the atmosphere. So why do we care about emitting CO2 to the atmosphere? And the UK is doing a really good job, actually, of starting to reduce our CO2 emissions. But most of the world's fuels or energy come from fossil fuels, which isn't sustainable. And what that does is, by burning fossil fuels, it emits CO2 to the atmosphere. And we know that concentrations in the atmosphere are increasing. So forming hundreds of thousands of years ago, we can look at ice cores, and we can look at pockets in that ice to work out what the atmospheric concentrations were like in the past. And more recently, we can make direct measurements of the atmosphere. So there's been a station on Mauna Loa, which we can see on the graph on this side here. These red points are all from the 1960s onwards. We're making direct measurements of CO2 concentrations in the atmosphere. And what we see is that CO2 concentrations have increased substantially since the Industrial Revolution in the 1800s. And that is a problem because CO2 and other greenhouse gases in the atmosphere essentially act like a blanket on the Earth, and whilst they allow sunlight and heat to pass to the Earth's surface, it then prevents it from getting back out into space. So we're gradually warming the Earth's climate, and that is a problem. And so the UK are leading the way in some respects in the way that they're developing net zero emissions legislation. So initially, the Climate Change Act came out. That was in the early 2000s. And since then, we've passed a net zero emissions law. That was done by Theresa May in 2019. It sort of flew past like a ship in the night. But it's legally binding, and it requires us to reduce all greenhouse gas emissions to net zero by 2050. And 2050 is actually not very far away. That's, 25 years is going to pass by very rapidly in terms of the rate of change that we can make to this type of infrastructure. And so these are some of the technologies that we could use in order to prevent us emitting CO2. But this is where we've got to get to, which is going to be quite a challenge. So how are we going to do this? And I guess I've already sort of started to talk about some of the answers here. We've got many low-carbon technologies, and some of these have been known about for a long time. So in the top right-hand corner there, that's De Noordweg pumped hydro storage. That's a great way of taking energy from a time when we're producing lots of it, storing it, and then releasing it when we need it. So pumped storage is a really good way of helping our energy system to be more agile. And you can combine that with other types of renewable technology like solar and wind. More recently, the government is looking at hydrogen as a potential fuel, and we do need to have a solution for how we deal with domestic heating, because that will be a challenge. So producing the electricity that we need in large-scale power stations is relatively straightforward, but how we heat our homes will be more challenging. And at the moment, most people do that domestically with gas. But let's try and solve one challenge at a time. And so let's think first of all about the energy that we get coming out of our power sockets, so the electricity that we need for society. And so nuclear, as I've said before, is a really good option for us to be able to do that, because whilst waste is produced, we have quite a lot of reserves of the materials that you would need to put into the nuclear power station, so uranium or thorium, depending on the generation of your reactor. And we've got quite a lot of, well, we certainly did have quite a lot of expertise in building nuclear power stations. So Calder Hall in 1954 was the first operating nuclear power station. The site's now Sellafield, and that's where, at the moment, we are keeping a lot of our radioactive waste. But we have power stations all over the country that are in various states of generation or they're starting to be decommissioned. But we've got lots of good sites, so I don't know how much you all know about nuclear power stations. This is a nuclear power station quiz. Does anybody know or recognise any of these nuclear power stations? Recognise all number 4? Yeah. Charles Vynnedd, very good. That one's in Wales. The others are in England. 2 are in England, 1 is in Scotland. They're Heysham in Lancashire, Hartlepool, Charles Vynnedd and Torness. So these stations, not all of these are operating. Which one is not operating? Charles Vynnedd, very good. Okay, so these are this is actually from 2022, so this is 3 years ago. This is not totally up to date, but these are the sites of active decommissioned and planned nuclear reactor sites. So at the moment, the closest ones to where we are Hinkley, and Hinkley is planned for a new reactor, as is Sizewell. But we've got a lot of coastline. For nuclear power stations, you need water. So there are many places that are actually quite good to put nuclear power stations. So we need reliable, affordable, low-carbon power. That's the reason for trying to do any of the work that I do. Nuclear power offers that low-carbon baseload, so it's a great option. And we've been doing it for long enough to know that it is proven to meet UK demand if we put our investment into building nuclear power stations. It also releases less radiation into the environment than other major energy sources, such as coal-fired power plants. So the emission of the gases from coal-fired power stations put particulates in the atmosphere, and that's also bad for your health. And so whilst nuclear often receives bad press because radiation seems dangerous, other sources are not better. And it can return a lot more power than renewable energies for the same area. So if we were to cover the whole of the UK in solar panels, we wouldn't produce enough power to meet the demand, where you only have to have a few nuclear power stations in order to be able to do that, because it produces a lot of energy. And then, interestingly, the government are also putting more emphasis on nuclear in their energy strategy. So at the moment, something like 18% of our energy mix is made up with nuclear, and the government are aiming to raise this to about 25%. John Armstrong in. Okay, so as I've said, nuclear power produces waste. So we've been producing energy through nuclear since the 50s. What waste do we already have that we have to dispose of? And then we need to think also about future waste if we go down a producing more energy from nuclear route. So there are 3 different types of waste, and the way that you deal with those wastes and want to dispose of them will be different, because those types of waste have different emission properties in terms of radioactivity and heat. So low-level waste is categorised as anything that's less than 4 gigabecquerels of alpha activity, or slightly more beta activity. So anything that's come into contact with other radioactive items often becomes radioactive waste itself. And a lot of this waste, so this is 93% of our current waste inventory by volume, a lot of that waste is not only associated with nuclear power stations, but also universities and hospitals. They make a lot of low and intermediate level waste. So intermediate level waste is our next category of waste. So that is classified as anything above 4 gigabecquerels of alpha activity or 12 gigabecquerels of beta or gamma activity. But intermediate waste is then separately classified from our last classification of waste because it doesn't generate heat. So this is 6% of the volume of our inventory of radioactive waste. So together, these 2 wastes comprise 99% of the waste that we have existing already that we need to dispose of. So that's quite clearly, by far, the huge majority of the waste that we have is low or intermediate level waste. And the way that you can deal with low and intermediate level waste is different to how we deal with high level waste and spent nuclear fuel, which comprises less than 1% of our inventory. But this is the bit that's really tricky, because this waste produces high levels of activity, but it also generates heat. And it's this stuff that we really need to build a geological repository for and store underground, away from the anthropogenic environment and away from any interaction with the groundwater sources that we might want to use or exploit. So we need to think of somewhere that we can put this waste that is so far away from any other activity that we'll want to use the subsurface or just immediately below the ground surface for. So to put that as a pie chart then, just to show you exactly how little that is in terms of volume, but how difficult it will be to deal with, that's our 1% of high-level waste at the top there. So what are the options for disposal? And intermediate level waste will probably be disposed of underground as well, and low-level waste will probably be disposed of in surface facilities. But high-level waste is what we're going to need to dispose of under the ground, and that's going to need to be at least 500 metres under the ground surface. So at present, all of our inventory is at Sellafield, and the way you deal with high-level waste, first of all, is that you vitrify it in glass, and then you encase that glass in a canister, and then at the moment we've put those canisters underwater, and they're in cooling ponds. And the reason for doing that is because spent nuclear fuel comes out of a reactor at about 600 degrees Celsius, and you can't put something at 600 degrees Celsius directly into the subsurface because you'll create all kinds of problems because it's so hot. So we need to let it cool down. So we do that in cooling ponds, and at the moment the radioactive waste management community think that about 100 degrees C is the upper threshold really for the temperature that we want to put material into the subsurface. Though there is work, and some of the work that I've been doing has been looking at what the effect of a temperature of 150 or 200 degrees C might be on the material behaviour that of the materials that we will use to store this waste in the subsurface would be if we were to increase the temperature. Because by elevating the temperature a little bit, or allowing your threshold to be a bit higher, it means you can get rid of the waste sooner, so it doesn't need to be sitting at the surface for so long, which would be advantageous. It also means that you can probably pack the waste a little bit closer together, so your repository footprint, when you build it, doesn't need to be so big, and that's also advantageous, both from an environmental perspective and from cost. So what are our long-term options then for disposing of this high-level waste? So there are a number of different concepts that different countries are coming up with for disposing of that waste, and the waste disposal concept will be a bit dependent on the geology that you've got, and I'll explain through the talk that actually the UK is really fortunate in the types of geology that we've got in order to allow disposal. But some countries only have a particular rock type, whether that's hard rock, crystalline materials, or whether it's a sort of soft rock, mud rock type bedrock. But in all of the concepts, you take the high level waste, you vitrify it, you pack it into copper canisters, they could be steel canisters, and then you put that into a small borehole that is then filled with an engineered barrier material around the waste package, and then each of those little boreholes are in a gallery tunnel. That tunnel is then backfilled with the same kind of backfill or buffer material, and then each of those tunnels is situated at least 450 or 500 metres below the ground surface in a bedrock that has particularly favourable geological properties for waste containment. So there's a number of different layers that are helping us prevent radionuclides from escaping from that waste package into the groundwater or into the subsurface environment, because that's what we want to avoid. So in the map on the left-hand side, you can see some of the countries that have got underground research labs. So the UK doesn't have an underground research lab yet. And part of the reason for that is that we've got a lot of different geologies that we could use where other countries don't have. And so they've set up underground research labs in that particular rock type that they're interested in, and they're doing research in that environment. And we can take the learnings from that research in order to help us develop our geological disposal facility. So in France, they've got Tournemire, Inclay and Bure, although since this figure was drawn, they've focused in on this site for their disposal concept. So this is in the Calovo-Oxfordian clay, and we have Calovo-Oxfordian clay in the UK, so that's a good site to compare research from and understand what they've learned. Belgium have Mol, and Belgium and the Netherlands are both looking at the boom clay, which is where Mol has been built, and this is a photograph of me visiting Mol. With the BGS, I'm very lucky to be able to go to a number of these underground research labs. So I've been to Bure and Mol. And the boom is really interesting. You can see from this photo at the bottom, if you take a plug out of the lining of this tunnel that they've made, it's about 250 metres underground, the boom clay will squeeze out of the hole like toothpaste. So it's a really plastic clay, it's really soft. And I have done some testing on the boom clay, though I'm not going to talk to you about that today. So it's a really pliable clay. This is Conrad. Sorry, I've gone away from the map here. In Germany, we've got Conrad and Gorsleben. Gorleben is in salt, which is another rock type that the UK has access to, though at the moment there are few concepts that are really thinking about evaporites as a host rock, because it's additionally complicated because it can creep as a material. So if you open up a gallery inside a salt deposit, the walls will start to close again over a period of decades, and so if you pack waste into there, you are eventually going to be squashing it in a way that you wouldn't in a harder sedimentary, like a mud rock type geology, if that was where your disposal concept was built. Now, Conrad is an old iron ore mine, and that's in Jurassic sediment, and I've been to Conrad too. Conrad is interesting because it's right next door to another mine called Assa, which was a salt mine that has had radioactive waste disposed of in it. And Assa, unfortunately, when it was excavated, because it sits underneath the Rotliegend sandstone, which is the equivalent to the Bunter sandstone in the UK, they didn't leave very much gap between the top of the salt deposit, it's a domal salt, and the sandstones above. So essentially lots of the water of the North Sea is now migrating its way into the salt mine. And if you imagine if you mix water with salt, what you get is dissolution. So the mine is really unstable, and it's been packed full of radioactive waste since the 60s, and at the moment they're backfilling it with concrete to stabilise it, and they will excavate all of it once Conrad is built and move it from one facility into the other, because Assa is not stable. So that is learning that we can apply to the UK case if we're looking at evaporites, though our evaporites are mostly bedded deposits, where in Germany they've got a lot more domal salt. And then moving up into Scandinavia, Sweden and Finland are, I guess, more advanced in their disposal concepts in that they've identified sites. Finland has started building their site at the Olkiluoto. It was an old nuclear power site, and that's in granodiorite. Sweden also has the same. It's got granite host rock, so they're hard rock crystalline geology. And the challenges with using a hard rock geology versus something like the Boone clay, which is really plastic and self-sealing, will be very different, because, as you can imagine, with a crystalline geology, the primary permeability, so how easily the fluid can get through the matrix of granite is really low. It's not easy to pass fluid through a granite, but granites are full of fractures, so the secondary permeability is quite high, so you have to be able to deal with that if you're going to construct a repository in that type of environment. So this is Conrad, and this is Espa. I've not been to Espa, which is the Swedish underground research lab where they're going to build their repository. I've always been very envious of the people that have been able to go there, because the BGS did a lot of work with Espa through the last sort of decade or so. And then this is an underground research lab that was not on that map. This is Bukov in the Czech Republic, and this is another crystalline geology. So the same hard rock challenges as Scandinavia will have in building their repository. Their underground research lab at the moment is in an old uranium mine. So the UK can look at the mining sites that we've got and potentially use those for research in order to understand the material properties at depth before we construct an underground research lab or the final disposal facility for the UK waste. So, as I mentioned, the UK does have a range of geologies that would be appropriate to use for radioactive waste disposal. We have granites, we have mud rocks and clay stones that have appropriate permeabilities that we could use as our host rock for our repository. We also have evaporites. The evaporite deposits are quite thin, certainly onshore. So we have Permian halite up in North Yorkshire, and we have Triassic halites sort of around Cheshire and into the East Irish Sea that we could use. And certainly for the Permian halites, they get a lot thicker offshore, and the Permian halites are the same stratigraphic sequence, the Zechstein sequences, as we see in Germany. So a lot of the learning from Germany could be directly applied to using those in the UK. But these rock types are all typical of those that are being considered in other countries. So we're fortunate in that we have a wealth of great geology that we could use, but that also makes refining the site that we will use potentially more challenging. And the organisation that is responsible for deciding where our radioactive waste will go is called Nuclear Waste Services. They're an arm of the Nuclear Decommissioning Authority, and their process to identify a site at the moment is very community driven, so they require communities to volunteer to host the site. And at present there are 2 communities that are on their list of communities to work with to identify the site. At one point there were 4. One was excluded because the geology wasn't good enough. So the process is that the community volunteers, NWS and the UK government invest in that community in terms of helping the community build infrastructure, and then they also do a number of initial scoping studies on the geology to make sure that they're happy that that community would have a geology that could be used. And then as they go further down the road, we'll start drilling boreholes. Eventually a site will be selected for building an underground research lab, and then we will take that forward to constructing the repository if what we understand from the research lab is basically good enough. But at any point the community can withdraw. So we also lost, we did have 3 communities over in Cumbria that for which the primary geologies were the Borrowdale Volcanic Group and the Mercia Mudstone. And the Mercia Mudstone is interesting because we have the Mercia Mudstone underneath us in Cardiff. But as I'll explain through some of the work that I've been doing, working with materials that have got evaporites in them can present other challenges, not only from a point of view of creep, but also because the groundwater in them will be quite saline. And so we lost one of the 3 communities over here through the geology being inappropriate. But we did have a community over in Lincolnshire called Thedlethorpe that was, the primary geologies would have been the Lias, the Oxfordian clays. And that geologically would have been probably better, but the community decided to withdraw because they weren't really a community with nuclear power previous history. They had a sort of a gas, they were sort of gas turbine generating infrastructure, and so whilst the community was used to industrial plant, they weren't really used to the idea of radioactivity, and then there were political decisions that meant that they withdrew from the process, which is a shame. I think it would be good for the UK to have a community that was in a different geology to the Mercia Mudstone, because that will give us more flexibility in the future for choosing a site that's geologically the best site. But we are fortunate in that we don't have to really deal with things like significant tectonism, or significant volcanism. So I am working at the moment with the Japanese Nuclear Waste Management Organisation on a study that is trying to identify the risks around putting their nuclear waste in a particular couple of sites that are, again, old nuclear power station sites, and the Japanese have got a lot of nuclear inventory, but they have to deal with the fact that they are on an arc, and so they have a lot of volcanism, and they also have a lot of tectonically active large-scale crustal faults. So that's a problem that we don't have to deal with, which is great for us. So what do we need to know about the geology if we're going to identify a site and put the waste there? So this is a piece of bentonite, but it could be any type of host rock, I guess. So we need to know how easily fluid will migrate through it. And what we want to find is a material where the permeability is really low. But we also want to know how it will behave if it's subjected to heat and if it dries out, because the radioactive waste will generate gas. There'll be a gas generation phase early on, and there'll also be a heating phase where it's sort of cooling down. So the heat and the gas generation will affect the material, and that might impact on the way it seals around the radioactive waste, which is what we want it to do. And then also the chemistry of the groundwater might make a difference to the behaviour of the material. So we want to understand about what the groundwater chemistry is likely to be, and whether or not it will stay the same for sort of 1 million years into the future, because that's roughly the length of time that we want to make sure that this waste is isolated for. So how do I learn about those properties? And as I said at the beginning of the talk, I've become an experimentalist that looks at real rocks now. And the way that we can do that is by taking a piece of the material and essentially putting it in a piece of apparatus that isolates it from the surrounding environment but pressurizes it to an in situ pressure that you would experience at the right depths under the ground surface, and then allows fluid to pass through it. So this is a simple type of apparatus that I would call an isotropic apparatus, because the sample, this is our material, sits in between two steel ends that supply fluid to it, one at each end, and it's isolated with a Teflon sheath, so that keeps that doesn't allow any fluid to get into the sides of the sample. And then that sample, this is actually upside down, it would hang in a fluid. So that fluid you can pressurise and put a confining pressure on your sample hanging in the apparatus. So that allows you to make sure that the pressure that you're running your experiment at is realistic for the rock conditions, but also it means that you can, if the sample has any kind of swelling clays in it, you can sort of stop them expanding by applying the right confining pressure to the outside. And then you pass the fluid through it. And this takes a long time because these materials are very low permeability. And this type of test, although it takes a long time, gives you important results, because this is what we would call a steady state test. So in the oil industry, you might measure the permeability of a cap rock by pulsing pressure. So pulse permeometry is another type of testing for working out how permeable something is. So you suddenly increase the pressure and you look at the pressure decay, and then you can use Darcy's law to work out what the permeability is. But this is a steady state type of test, and I think it's better because you don't stress your material. You can do it over a long period of time. You can have a very small pressure gradient, and as long as you can measure the volume of fluid that is passing through very accurately, then you can work out what the permeability is. So the accurate volume measurement is really, really important for this type of test. So I did this type of test on the... How do I get this to go away? Okay, well you can't read it, sorry. This is the Bruce nuclear site in Canada, which is it's in Ontario, it's here. And Bruce is one of the sites that Canada are considering for disposing of their radioactive waste, and they've got a couple of formations, the Queenston Formation and the Cobalt Formation. They're limestones, but they're really, really tight, and they're also quite deep, and they are the groundwater that moves through them is really old, so it's quite saline. So they were interesting to run tests on. They nearly ruined the apparatus because if you put really saline fluids inside very highly polished bores of steel cylinders to have very careful volume measurement, it tends to eat and corrode the inside of the apparatus, which is not ideal. But what these graphs are showing you is the volume inside the pump on one side of the sample and the volume in the pump on the other side of the sample. So you would have three pumps, one to compress the fluid inside your vessel, and then one pump connected to each end of the sample. And so you can introduce a very small pressure gradient across your sample and then measure the volume change. And so this is nice and linear. That allows us to use Darcy's law. We know the cross-sectional area of the sample, we know its length, we know the properties of the fluid, and we know the small pressure gradient that we've put across the sample. We can measure the flow rate, and then we can calculate permeability. So we did that at the survey, and we measured the permeabilities then on these two host rocks as of the order of 1 × 10 to the minus 22 metres squared. So that's nano Darcy. So it's really, really low permeability. So this will be a good host rock for the Canadians to use, as long as some of the issues around the salinity of the groundwater can be fixed for their barrier materials. So coming back to the design then, we have our host rock, which could be any number of bedrock geologies, and the UK's got a huge array. But we also need this material, this engineered barrier, to sit around the copper canisters and to backfill the tunnels and the galleries in our repository design. And we also need that material to be low permeability and unable to transmit or can prevent the transmission of radionuclides so that we don't have escape into the environment. So that material is what I've spent most of my last few years researching. And the type of material that most designs are looking at is something called a bentonite. And there are different compositions of bentonite, but usually they're either calcium-rich bentonites or sodium-rich bentonites. Bentonite is a good material to use because it has a really high swelling capacity. So you expose it to any water and it goes pop. And I should really have included a little video that I have of a tiny piece of bentonite in a huge fish tank. And if you watch it over a long period of time, it grows to many orders of magnitude bigger than the size it started. So it has this huge capacity for swelling, which is good because it means that you can put it in a void space, let it get a bit wet, which it will do from the host rock around it as it absorbs groundwater, and then it will expand and fill any cracks and crevices in your design. So if you've got a geology that's crystalline with a high secondary permeability, having a material that can expand and fill those fractures is really advantageous. So our disposal safety case then needs a bedrock geology and it needs an engineered barrier. So this is what bentonite looks like, and the disposal cases that are being considered think of bentonite going into those holes either as a pre-compacted material already made up, or as slightly smaller scale bricks, or it could be pelletized, so essentially looking like cat litter that you might put in the hole and then allow to expand, or as a powder even. So different designs have different ways of incorporating the bentonite, but I've so far been studying bentonite as pre-compacted blocks and looking at how it will expand and fill small gaps. So there are going to be some challenges with using bentonite because as it expands, it doesn't always do it in a uniform way, and that will be a challenge because if it doesn't expand in a uniform way, because as the water migrates into it, the first parts are expanding and reducing the permeability so that more water can't get in to the middle portions, then you will get variations in density across the material in the hole. You'll also get variations in permeability, and then you'll get variations in the mechanical properties because it will be stronger in parts and imposing a larger swelling pressure in parts of the material than it does in others. So that material heterogeneity could be a problem. So that was really the driving force behind a number of these experiments, understanding what the material heterogeneity was and whether or not that would be a significant issue for usage of bentonite in the designs. So heterogeneity may adversely affect the long-term behaviour. So it's really key if you want to assess how it can be used in a safety case for the geological disposal. So the types of experiment then I'm going to show you some of the results of were to look at the expansion of bentonite into a void space. So this is really an end member case. You never have a void space that was on the order of the same size as the material that you put into the hole. But we started with samples that were nearly half the length of, or just over half the length of the whole of the inside of an apparatus. And we filled the other half, the void space, with a groundwater composition fluid or with deionized water, depending on the test we were running. And then over time looked at how that sample expanded to start from this size to become this size in that void space. And then what that did to the material properties, and then what stresses and pressures that imposed on the surrounding apparatus to understand what it would do in the repository hole. So we were looking at swelling capacity as a function of the axial swelling strain, so how much it can expand along its length. And we did that at ambient temperature and at elevated temperature and looked at salty groundwaters. So this is what the apparatus looks like, and this is what I'm trying to build in the basement. And as you can possibly understand, this is big, heavy, it's a lot of steel, it's bespoke. And so this is the apparatus that lives at the BGS. And the Fluids Processes group there have a fantastic setup with a lot of kit It's been built over the last 3 decades with a lot of investment as well, because these things are not cheap. So you need to have a syringe pump at each end of your sample to control the volume and the pressure of the fluid entering the sample. And those syringe pumps have to be extremely high resolution. So these particular syringe pumps come from a company called Teledyne in America, and they're about 40k each to buy, so they're quite expensive, and all of the parts on them can break and are also expensive. So I try to be very careful of the few that I now have in the basement. But the way they work is that they've got an optically encoded disc that's inside that rotates to allow a syringe to move up and down this barrel, and it has increments of about 16 nanolitres, so it's really small, the increments that it can measure in volume change. So the sample sits inside here. I don't know if I've got cut through. No. Okay, so the sample sits inside here. This is a steel cylinder. Its walls are about 5 or 6 centimetres thick, so it's a really heavy lump of steel. And you have quite a small test sample, really, compared to the size of the apparatus, that you push into the hole and then fill the top up with fluid, and then put an end closure top and bottom to keep it contained. And this particular apparatus has a load of sensors around the outside so that we can measure a few things that are important for us to understand. So as well as measuring the volume and the pressure change in the fluids, top and bottom, using the syringe pumps, we can also measure the pore pressure, so the fluid pressure in the vessel along its length. So if you imagine the enclosure sits inside, the test sort of volume finishes about here and starts about here. So we've only got about 12 centimetres in the middle of void space inside this apparatus. And along that length, I've got positioned 3 different layers of pore pressure sensors. So that's 12 tiny little holes through the vessel that allow fluid to come out for me to measure the pressure of those fluids using these pressure transducers. And then at the same time, there are 1 top and bottom and then 3 radially around the bore of the vessel stress sensors. So these measure from the face of the clay, they measure the expansion of the clay. So they've got a membrane that deflects to allow you to measure what the pressure the clay is putting directly on the surrounding environment. So those things are important. They tell us the swelling pressure of the clay, and they tell us the fluid pressure and the way the clay is expanding. So I guess this is perhaps too much detail, but this is the list of the types of tests, the setup, so different starting sample lengths, different void spaces, different dry densities. So the dry density of the material is essentially how much clay is packed into the same kind of volume of samples. So if your dry density is high, you've compacted a lot of clay into that volume. If your dry density is a bit lower, you have compacted less clay into the same volume of starting sample. And then I tested different types of bentonite. So there are calcium-rich bentonites, there are sodium-rich bentonites. How do they react differently under different conditions? And looked at saline waters as well as deionized water as the test fluid. So, big array of tests. Most of this was funded by the European Joint Programme on Radioactive Waste, which ran from about 2019 to 2024. And before that, a precursor project that was also European Union funded on bentonite mechanical evolution. And so this is the type of output that you would get from those sensors. It looks complicated, it's not really. These lines all are telling you how much swelling pressure the sensor around the outside of the clay is receiving. Some of these graphs have got more sensors on them because I showed you one apparatus, I had 3 different types of apparatus, and on some of those apparatuses I had more swelling pressure sites of measurement. But the take-homes, the important take-homes, what it shows you is that, first of all, swelling pressure peaks and then it decays and comes down to a constant level. And the constant level is kind of what you want, because that's like in perpetuity the swelling pressure that material is putting on the surrounding environment. What it's also showing you, I don't know if this is my first arrow. Okay, so it's showing you that you don't get much swelling pressure. Once you've had that peak and you've decayed to an asymptote, you don't get much swelling pressure change, which is good. And we ran these tests each for 100 days. Obviously, that's a minuscule amount of time in the length of time that the radioactive waste would spend underground. So what we don't really want to see is that these lines are not all on top of one another. So really what we want to see is that the bentonite puts the same swelling pressure on every single sensor because it's homogenised, and so all the pressure is the same regardless of where you are in the material. So what we do see is persistent heterogeneity, and it looks like these lines are almost never going to asymptote, or at least they're not going to asymptote for many years, which is a challenge that we need to think about when we're putting bentonite in the ground then, if it's not going to totally homogenise. What we also saw was when we elevated the temperature, so these ones are the top three graphs here in the green are at 20 degrees C. As we elevate our temperature, so we're running tests at 100 degrees and 150 degrees, the peak tends to become much lower, so we don't get that initial peak, it just sort of arrives at a swelling pressure, which is potentially a good thing. And then if we reduce the dry density, so some samples we started with a dry density of 1.7 grams per centimetre cubed of well, that's the density, so how much clay you can squish into the same starting sample length. So these four tests were all 95 millimetres long to begin with. If we reduce the dry density to 1.5 grams per centimetre cubed, so same starting sample size but just less clay material in that compacted initial sample size, we see obviously a lower peak and then a reduced swelling pressure. And you would exactly expect that because you've got less clay inside the body of the vessel, so at the end of the test there's less material to be placing swelling pressure on the surrounding apparatus. And what we did see that was also interesting was that at the highest temperatures, we're seeing potentially a degradation in the swelling pressure. So swelling pressure starts, peaks and asymptotes, and it starts at this level, but then it's gradually tailing off. And we don't really want to see that either. We want to see a constant swelling pressure maintained in the material. So potentially 150 degrees is not a good temperature to go to, is what that's telling us. We also looked at then a saline fluid, and this became really interesting. So these are all 1.7 dry density clay samples, different lengths. We see the same complexity in the different swelling pressure sensors towards the end of our test, but we see a reduced peak with a saline fluid. So we pass a really salty water through it. We don't get so much of a peak, but it does expand to fill the volume. But if we increase to 3 molar NaCl, and 3 molar NaCl is close to the composition that the Bruce nuclear site had for their groundwater, we see almost no peak and almost no swelling pressure generated at the end. So the material does expand to totally fill the volume, but it doesn't put any swelling pressure on the sensors, and that's really interesting. So when I took the lid off, this is what the sample looked like. It didn't look like a competent cylinder of bentonite that just expanded to fill the volume, which almost all of them did. It looked like a slurry. I had to jump backwards when I took the lid off because it poured out and I wasn't expecting it, and it went everywhere. So 3 molar NaCl is going to be a real problem for bentonite. If we choose a geology as our host rock that is full of evaporites and therefore the groundwater is really salty and it's anywhere near 3 molar NaCl, bentonite expansion, bentonite will expand, but it will not place a swelling pressure on the surrounding environment, and it will not be competent. And so that is a challenge. And since doing these tests, NWS have taken a look at this and said, eek, that might be a problem because at the moment our two communities are in the Mercia mudstone, and the Mercia mudstone is full of halite layers and it's got a salty groundwater composition. So they've since invested in a lot of research and funded some PhDs looking at the Mercia mudstone, looking at salty environments and looking at the effect of salinity on a number of different properties of both the host rock and the bentonite. So it's had a bit of an impact, really. So as well as measuring the swelling pressure, then we also can look at the pore pressure, and those pore pressure sensors essentially tell us how quickly that sample is expanding through the void. So when you put the sample in the void, it covers some of the pore pressure sensors. and some of them are exposed because those pore pressure sensors are in the bit that was fluid at the top. And so when you place a pressure then at both ends, the pressure in the fluid is instantly transmitted. So the pore pressure sensors that are in the fluid are immediately at maximum pressure, which in this case was 5 MPa. But the sensors further down the vessel that were covered by clay to begin with need to wait until the fluid's migrated through the clay to reach the sensor before they can start receiving a signal. So when the sample is smallest, we see the pore pressure reach maximum most quickly because the fluid gets into the sample more quickly. There's less sample for it to migrate through, and so actually that tells us that the whole sample is really, water is getting through the whole sample within a few days, like maybe 10 days, the pore pressures are equilibrated. When the sample is 85 mil long, it takes a lot longer. It takes nearly 50 days for the fluid to have got into the middle of the sample and for those pore pressure sensors to start reading fluid pressure at the same pressure as what we're placing on the sample at each end. So those pore pressures equilibrate fastest, so they all get to the same level fastest at the highest axial strain. So that's the smallest sample, the largest amount of axial length expansion, and we see that regardless of the conditions that we impose. So it responds pretty quickly to fluid infiltration, but the material properties don't respond quickly to fluid infiltration. So whilst we see the pore pressures equilibrate, we don't see the swelling pressures equilibrate, and that's interesting. So we see a low rate of change then once the pore pressures have equilibrated, they've equilibrated, nothing happens. And the slowest response we see at the pressure transducers furthest from an inlet of fluid. So as you would expect, if the sensor is right in the middle of the vessel and that part is covered with the most clay, it'll take the longest for the fluid to get there. Okay. So let me move on then, because I'm rapidly running out of time, to the last thing that we can do once we've run a test and disassembled it, is we can understand what the moisture content is in the final sample. So this is a sample of bentonite that I've put in an apparatus. It's expanded, so now it's full length. It would have started at sort of 65 centimetres long. It's expanded. It still looks pretty competent because I used deionised water for this test, not the saline fluid. Once we've removed it from the vessel, we can slice it and oven dry it to see what the moisture content is in chunks along its length. So I did that for every 10 centimetres along the length of the sample, and then you can plot that as a distance from the base, which is, I guess, where the clay would have started at the beginning. So these samples up here look really cracked because they've lost a lot of water. The samples at the bottom don't look very cracked at all because more of the clay material was still sitting at the base of the vessel after the expansion had taken place, and the clay doesn't migrate or move up and down the vessel very well. So this is showing us still we've got quite a lot of material heterogeneity. So if we increase the salinity, we get more moisture at the bottom and a bit less at the top. But we are missing information from the very top because it was totally slushy for a lot of the samples where I used a saline fluid as the test fluid. And you can see that this is axial strain, so that's the amount of swelling along the length that the sample has done. So these are small starting sample lengths, these are much longer starting sample lengths, and the BGS, since I've left, has been filling in information here for samples that are much closer to what you would expect a realistic condition would be in a geological disposal environment where you have quite a lot of clay and quite small holes, really. So these were really end member tests. This is really probably more like what natural conditions will be in a disposal environment. So we get more pressure difference between the top and the bottom of the sample when you've got a longer starting sample. So more it takes longer to make the sample more homogeneous when you've got more clay. And with 1 molar NaCl, you really do not have very much swelling pressure at that end where it's expanded, so that could be a problem. And then if we increase the temperature, that also changes the way we see moisture content distributed through the sample. And if we increase the dry density, so use more clay in a sample, that reduces the variation along the sample length. So that's potentially a way that we can combat these issues with heterogeneity, increase the dry density. Okay, so this is essentially showing us the same pattern of data as we saw with this, high salinity samples. 150 degrees C, swelling pressure seems to have reduced at this end, which is a problem. So again, really high temperatures, we probably don't want to go there. So a threshold of 100 degrees C is probably realistic for what we want to do with disposing of our waste. So bringing this back then to the environment that we will be using this material in, we can use pore pressure and swelling pressure and moisture content to understand how this material will behave before and after swelling when it's exposed to groundwater in a disposal environment. We see that decreasing the dry density reduces the overall swelling pressure, so that's potentially a problem. So we might want to stay on the 1.5, 1.7 grams per centimetre cube dry densities and not go down to 1.3, which some countries are considering. And increasing the temperature reduces the residual swelling pressure, and saline fluids make a really big difference to how competent that bentonite is once you've expanded it. And so really we want to stay away from environments that are strongly saline. So that's a strong motivator to try and find a community in an environment that doesn't only have the Mercia mudstone as their deposition host rock. So what we've learned is that pore pressure equilibrates, swelling pressure and moisture content show us that we have material heterogeneity, and they're challenges that we need to deal with. At elevated temperature, below 150 degrees C, our swelling pressure and peak values are suppressed, our swelling pressure equilibrates faster, and so both of those things are good for disposal. And we see a slightly higher uniformity in the moisture content, so slightly flatter profile, less of a curve. And then using elevated salinity fluids is problematic because although the swelling pressures equilibrate faster and we see a reduced peak, which is good, actually when you open up the test and you look at the material, it's not competent at all. And so that will be an issue if we use it in a repository that has strongly saline groundwaters. But in all cases, the stress that we saw at the end of tests when we measured the swelling pressure were variable, like it didn't homogenise, and how acceptable are the differences? More work needs to be done there, and we need to understand potentially what the even longer term would be, though I can't see labs wanting to run tests for more than 100 days because it occupies apparatus for a very long time. You don't get many tests in a year. So it's possible that low density zones, voids in the host rock may help with homogenisation locally because it reduces the dry density, and then you get an interplay between the material that's homogenising but also having a high enough swelling pressure to seal the material in, and you want a low enough permeability. So bentonite can be designed to allow for variance, and all of these tests I've run on compacted bentonite. I haven't run any tests using powders or pellets, and what kind of a difference does that make to the way it behaves? There will be some difference, and some groups are starting to do that. I know the BGS were running tests that were part compacted, part pelletized bentonites, and looking at the variance there, but I've not seen the results from those tests yet. But what we did essentially was build a large data set, test a very large number of variables, and I've shown you the results for swelling pressure and pore pressure evolution, but there are lots of other things that we have done and could do, and we can look at the fluids in and out, we can look at strain data, we have done post-test geotechnical measurements, and I've not presented any of those today. But what the results are really telling us is that MX80, so that's the sodium bentonite, that I've tested, is able to close voids, it's able to be used in a repository, but depending on the properties, depending on the parameters, so the temperature, the swelling pressure, the salinity, and the dry density, that can change the properties. So that needs to be accounted for when we're making a repository design. And so we do need to do further work there, and there are a couple of EPSRC funded projects that are ongoing at the moment that I know the survey is still working on with this apparatus. So more results are going to come soon in the sort of not very much axial swelling, smaller void type tests. So that will be important for us to understand the picture further. So thank you.